Hello, fellow mathematicians. You may have heard of Fourier Transform before, whether you're interested in physics or math or engineering. But no matter what you take interest in, and no matter whether you've even heard of it before, when you do learn about Fourier Transform, your mind will be blown. Because it's all of the things that makes calculus so cool and fascinating, and all of the things that make trigonometry so cool and fascinating, and all of the things that make math ubiquitous, coming together into this one super powerful tool. And this tool is applicable everywhere. This tool governs the sound with which you hear me right now, the light with which you see me right now. It governs the background music that should be playing right now. Fourier Transform is what makes math so cool and so awesome, embodied in this one concept. And that's exactly why, if you want your mind to be blown, then we're diving in right now. So first, let's review the concepts and ideas of the Fourier Transform so we can transition into actually applying it to the real world. So first, let's look at the formula. The formula for the Fourier Transform is g of omega equals integral from negative infinity to infinity of f of t times e to the negative I omega t dt. Let's start out with the function f of t. And f of t is some kind of signal. So in the real world, this would be something like a musical instrument playing a note, a sound, maybe anything that propagates as a wave that can be recorded as a signal with its intensity as a function of time. So this is its intensity at each point in time. And then the idea of the Fourier Transform is that we're going to transform this function with one domain, in this case time, to another domain. In this case, a function of omega. And omega is frequency. So what's going to happen is we're going to have a new function, g of omega, which will look something like this. And this function is going to have these peaks. And these peaks will correspond to frequencies that comprise the original function. For example, if this function is a sum of frequencies of like 5 and 8, then these peaks will be at 5 and at 8. And this is truly the power of the Fourier Transform, because you can take this signal that you know nothing about, and you can take the integral, and you will have these peaks pointing to the frequencies. And now you can bring out a certain frequency and bring down another one. You can edit the signal. You can change things. And this is why it's so important, because in all of math and all of physics, in sound design, in music, Fourier Transform is an underlying essential concept. And so how does this integral even do this? What is the mechanism behind this? Well, you'll notice that we're integrating with respect to time. So in this case, omega is just a constant. And this integral is from negative infinity to infinity. So when we integrate, we're going to take the limit as t goes to infinity and negative infinity. And so t is going to go away because it's going to go into the limit. And we're going to be left with omega. And thus we'll have a function of omega. But there's a very important distinction to make. Because imagine instead of integrating from negative infinity to infinity, we integrated from like negative 2 pi to 2 pi. Then we'll be integrating with finite bounds, and we're going to get finite values. So what's going to happen is we're going to get something like this. This is a finite function, and it's going to have these little peaks at the frequencies. These peaks, the coordinates of their high point, is not going to be precisely at 5 something. It's going to be actually at 5.01 so on, something like that. But it's going to be off by a little bit. And same thing for this one. So this is an approximation with finite bounds. So then let's suppose we bring up these bounds to like negative 4 pi and 4 pi. So they're a bit bigger. Then we'll have a function with taller peaks. And they're going to be closer, maybe at like 5.05 something. But they're still not going to be perfect. And these peaks, they're going to be taller and they're going to be thinner. So imagine what happens when we bring this to infinity. Well, when we bring this to infinity, g of omega will be basically a direct delta function, which is a function which is 0, 0, 0, and then it shoots up to infinity, and then 0, and it shoots up to infinity. So these are getting taller and taller and thinner until we get this infinitely thin and infinitely tall peak. And guess what? This peak is going to be perfectly centered at 5 and 8. So the idea is that this is the fundamental idea of calculus, and Fourier transform mirrors this, where you have a good approximation, but as you bring it to infinity, you get a perfect result. This is the principle behind derivatives, behind integrals, and this is the idea behind Fourier transform. So now that we understand this concept, let's actually think about how we're going to apply it to the real world. Because in the last video, we had cosine of x, and we took the Fourier transform of that. And cosine, it's a periodic function. It goes on and on in a pattern. So when you integrate it from negative infinity to infinity, you might get some kind of reasonable result because it goes on in a pattern. But we didn't want to integrate from negative infinity to infinity. So we made it aperiodic by restricting it and integrating it from negative 2 pi to 2 pi. And because the bounds were finite, we got something like this. But in the real world, you are not going to know what f of t is. The only thing you know is its value at each point in time, its intensity at each point in time. You don't know how to define it, what it's written as. You know that it's a sum of sines and cosines, but other than that, you don't know. And the point of the Fourier transform is to figure out what that function is. So if we don't know what the function is, how are we going to integrate it? Well, that's what we're going to learn today. So we're starting out with our f of t function. So remember that we don't know the frequencies that comprise this. We only know its intensity at each point in time. So in the real world, imagine a musical instrument. We're playing a note, or a chord of several notes. Then the only thing we would know is what our device would pick up, which is this graph, the intensity at each point in time. So you may remember from the last video that f of t times e to the negative I omega t term can be split into a real part and an imaginary part due to the fact that e to the negative I omega t term is analogous to Euler's formula. So let's start out with the imaginary part. So we'll call it I of t for organization, and it'll be f of t times sine of negative omega t. And here we'll just use w for omega. And then we have the real part, r of t, equals f of t times cosine of negative omega t. So let's look at each part of the function individually, starting with the imaginary part. So remember that the Fourier transform, it transforms our function from one domain, f of t, to another function with another domain, in this case, g of omega. And g of omega is going to depend on that integral. So as we sweep omega, I of t and r of t and f of t are going to change. And the area under the curve, the integral, are going to change as well. So when we sweep omega, we have to pay attention to the area under the curve because that is literally what is going to affect g of omega. So let's start moving omega around. Let's start just sweeping omega and see what happens. How does the area under the curve change? You can see that most of the time, the function I of t is kind of symmetric about the x-axis. So when we integrate from negative infinity to infinity, it'll all cancel out and we'll get 0. And when we integrate from like negative 2 pi to 2 pi, we're going to get a pretty small value. And so you can see that as we sweep omega here, it's going to pretty much cancel out. But let's keep sweeping it. Then all of a sudden, look what happens. When omega reaches 4, this will all line up under the x-axis. So when we think about what this will translate to in terms of the integral is going to be a large negative value. So when we integrate from negative infinity to infinity, this will shoot down to negative infinity in a direct delta. And you can see that this happens at omega equals 4. So we can start guessing that maybe one of our frequencies is omega equals 4. So let's keep experimenting. So you can see that it cancels out very nicely here. But then we reach omega equals 7. And look, it lines up again. The area under that curve is going to equal to negative infinity, and it's going to go into a direct delta when we integrate from negative infinity to infinity. So this happens at about omega equals 7. So already, just by looking at how this function behaves and how the area under the curve behaves as we sweep omega, we can already start guessing the frequencies. So let's actually test this. But before that, we're going to try R of t. And R of t has a very obvious flaw in that R of t is an odd function, meaning that if we integrate it from negative 2 pi to 2 pi or negative infinity to infinity, anything of the form negative a to a, it's symmetric integration, we're going to be left with 0 because it's going to cancel out. And so R of t is actually going to go to 0, and we don't really care about it. I of t is the one that will provide the change and the one that will provide the peaks. So when we integrate, we're only going to have to integrate I of t. So let's do that. We're going to create the function g of omega, and it's going to be the integral. Let's start out with finite bounds, like negative 2 pi and 2 pi, of f of t times sine of negative omega t dt. And bam, there we are. This function has two peaks at 4 and 7, the frequencies that we guessed would work out when we swept omega. Because when we were sweeping omega, it lined up under the curve there, and therefore we got a peak. And you can notice that in this case, the peaks are negative. Sometimes they're negative and sometimes they're positive. But the fact still stands that just by sweeping omega, we were able to figure out how the integral will behave. And finally, for the final component of the puzzle, let's change this negative 2 pi and 2 pi to negative a and a. And if we do that, and we slowly increase a, we're going to get something interesting. Because first of all, let's start out with a equals 2 pi. We're going to have these peaks. But you can see that they're not precisely at 4 and 7. For example, the peak at 4 is at 3.959. So it's going to be slightly off. But again, the idea of calculus is that as we take something to infinity, as we bring it to the limit, we're going to get a better and better approximation. So watch what happens when we increase a. We're going to increase it, and these peaks are going to get taller and taller and thinner, just as we predicted. And then when we bring a up to something like 10, you can see that these peaks are at 4.001. It's much closer to the value of 4. So if we were to bring a up to infinity and then integrate, we would have these giant direct deltas shooting down, and they would be centered precisely at 4. Isn't that incredible? So here we can see that using this function that we knew nothing about, by looking at the area under the curve and by looking at how we can take a limit and get a better and better approximation, we were able to figure out the frequencies that comprise it. And if I reveal to you the mystery frequencies, we can see that we were actually correct. Isn't that amazing? This feeling in math, when you realize that it all works out and that it all comes together and that the tools that you use have such a beautiful intuitive meaning, that is one of the most wonderful feelings in the world. As a final side note, you may have noticed that in real life, we can't take measurements at every infinitesimally small point in time. We wouldn't be able to record a continuous curve. We would actually record the intensity at discrete intervals, like this. And so, truly, the fully applicable version of the Fourier transform is the discrete Fourier transform, not the continuous Fourier transform. The discrete Fourier transform and the fast Fourier transform, which is a more computationally efficient version, are also very important tools. So, if you want me to make a video on that, please like and subscribe to this one. Thank you so much for watching. I really hope you enjoyed this video, and I would really appreciate it if you could like, subscribe, and share this video with all of your fellow mathematicians. Please watch another one of the videos that are recommended right now, and see you next time.